So it really is best to come to the live lecture if you can, in spite of the fact that the projector has a little green tint to it. But of course, sometimes you have to travel, and so treat the lecture videos as kind of a backup.
Is that slide gonna be in something you're sending us? Because I don't see
This was not in the pre-lecture notes? I didn't think so. That's all right. Everything I do here gets scanned and posted on Moodle, so you'll see it, right? Pre-lecture notes don't always happen also. Okay? And sometimes it just doesn't make sense to do them. Sometimes things change too quickly for us to get them in there. So let me move that around a little bit. This is the index of refraction that we talked about as a function of wavelength here. Wavelength, the symbol for wavelength is almost always lambda, like we had it before. Greek letter lambda. Right. And this one is in microns. Means 10 to the minus 6 meters. Another typical way of, let's see, I'm up here now. Another typical way of unit for wavelength is nanometers. It's 10 to the minus 9 meters. Okay, so the telecom industry right now, most of it is at 1.5 microns, which corresponds to, well, 1.55 microns is 1550 nanometers. But it started out at 1.3 microns, and we'll see why here in a minute, why they wanted to shift it. The key point for dispersion is that the index of refraction depends upon the wavelength that I'm at, the color. Okay? So you can see how dramatically it varies when I go to small wavelengths. Suddenly it just kind of goes crazy. Right? This means ditto index in depends on frequency is another way of saying it, right? Because frequency times wavelength, two different ways of specifying the same thing, because frequency times wavelength is a constant. That's Einstein's speed limit in empty space. Goes to c, like we talked about before. Right? So this is c divided by n. Questions on that? So here's a curve for the index of refraction for various types of glass. Borosilicate is really cheap. Let me, bear with me a second, I'm worried about where I am on the camera now. Make sure that's where I think it is. Okay, yeah. That one. Typical telecom grade optical fiber isn't on this curve. It's a little bit lower than this. So the index is about 1.44. Fiber. EG means for example. Single mode fiber. What's the typical Corning single mode fiber in the telecom industry? SMF 15, 16, 28? There's a variety of them. So for example, 16. Just a little aside there. Okay, so the index varies as a function of color, wavelength, or equivalently frequency. Now we get to one that you do have in your pre-lecture notes. So let me do that one this way. So different, we saw that v is the velocity, so if the index is changing, then the velocity is changing. Right? So different frequencies are going to propagate at different speeds. we mentioned that we have two types of velocities. One is phase velocity. That's the one that you're used to thinking of, all right? But for telecommunications, group velocity turns out to be the more important one for us. So, in terms of phase velocity, we can think of an unmodulated optical carrier. Carrier is like with AM and FM radio, when you tune to 90.1 or whatever it is, that's the carrier frequency of that signal. On top of that is some frequency bandwidth. That's the actual signal that's writing at the carrier frequency, right? Wi-Fi has a carrier frequency of 1.4 gigahertz. Okay, so that's what I mean by carrier frequency. If I don't modulate, then first of all, without any modulation, there's no information. So it's kind of a pointless thing, but it happens, right? There's sunlight isn't being modulated unless the atmosphere is doing something weird to it. Right? So we talked about refraction and how a straw looks bent when you stick it in a glass of water. Right? There's no modulation going on there, so that's being driven by phase velocity. So it's not like it's totally useless, but here's an unmodulated carrier. It's just a sine wave. So there's just one frequency or one color. Right? So think of these zero crossings. This is what we mean by phase velocity. These zero crossings are all moving at the phase velocity. I call it, I'll just write it out, V phase. Okay. So, and that is C divided by N. I'm going to go ahead and call this the direction. Z is usually the direction of propagation, and the phase velocity here is Einstein's speed limit, 3 times 10 to the 8 meters per second divided by the index of refraction. Okay, so index of refraction changing is going to change the phase velocity. But there's no information on this signal, right? This is just a tone. If you came into the room and I just sat here and went, am I conveying any information other than Shepard's gone crazy? Right? No, there's no information there, right? If I sing a song or if I'm speaking, that's a whole bunch of different frequencies that are changing, right? And if I shout, there's information in the amplitude, right? If I whisper, right? Now I'm amplitude modulating, right? If I go ooh, right? And I'm frequency modulating. Great. Guess we should have used the other tape after all. It didn't like my singing, eh? I'll take that as a critical note. Aren't you glad we tilted that thing up? Uh-oh. I think maybe I'll flatten it out again. Okay, let's pause.